Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic.
So, let's dig into this whole realm of machine learning and deep learning stuff with a sprinkle of intrusion detection applications. There's
absolutely.
a ton to unpack, right? We're basically looking at how machines learn from data and how different techniques shape what they do.
Right, and I noticed it kicks off with a clear distinction between types of machine learning. It's interesting that machine learning is defined as the ability of a machine to improve performance with experience. That's like when you keep practicing an operation until you've honed it down into almost a reflex.
Exactly. And then we move into the supervised versus unsupervised debate. Now, supervised learning means you have past observations or labeled data where both the features and targets are known. It's like having a teacher showing you what the right answer is.
And contrasting that, unsupervised learning only gives you the features, so you got to infer the structure and guess the targets, right? So
Right,
it's more
exactly.
about clustering or figuring out hidden patterns, like in customer segmentation.
And then we move into the slice of supervised learning problems. There's a neat split between classification and regression. Classification, as in saying yes or no, like spam detection or handwriting recognition, versus regression, where you predict a numerical value like estimating house prices.
Yeah, that's a clear way to think about it. Absolutely. And I really like the fingerprint example in criminal investigations. You know, even with identical twins having different fingerprints. That really emphasizes uniqueness in data patterns.
Yep, unique patterns are the bread and butter for these classification tasks indeed. Now, something that caught my eye was the hybrid methods that combine clustering with classification for supervised anomaly detection. I mean, it's like mixing a chef's spices just right. A little clustering to sort similar things, and a dash of classification to check if something's off.
And then there's regression for house prices. They even had that table with neighborhoods, school districts, and all that. Very practical, you know?
Yeah, it's like comparing apples to apples when you have clean input data. Right. And stepping into unsupervised learning, there's the whole idea of association rule discovery and sequential pattern discovery, which are super useful for things like product recommendations. It's like when you buy bread and then you're recommended butter, it's all about known patterns, even if they aren't explicitly taught.
That brings us to reinforcement learning. This area is really fascinating because it's about agents taking actions to maximize their cumulative rewards. Then they mentioned examples like robot movements and autonomous car driving.
Yep, reinforcement learning is kind of like training a pet. You reward the good behavior and eventually the behavior sticks. And here's a neat nugget, the idea of learning from experiences. Almost like how a football player learns shot outcomes over time. There's that video reference about Timo Boll versus Kuka, where machines learn from prior interactions. It sort of begs the question, can a machine really master something so inherently human?
True, but I wonder if we're sometimes overestimating how near machines are to truly learning like humans with experiences. I mean, everything is essentially data pattern matching, right?
I get what you're saying, but it's like the difference between rote memorization and genuine understanding in human learning. Right. It's like a machine's understanding is defined by its architecture and training, relying on huge volumes of data, not intuition like we have. Yet nowadays, deep learning is a powerhouse once you dial in all the right layers.
Speaking of layers, the deep learning part detailed the architecture with neural networks, how they mimic neurons and connections in the brain. It even touched on hidden layers and how features are built hierarchically.
Yep, exactly.
It's basically a series of transformations from simple to complex, making it a bit like stacking building blocks.
For sure. And then there's the bit about the limits of deep neural networks. Not only is scalability a huge issue, but you also can't just toss in 10x more data and expect 10x the precision.
Yeah, that's a great point.
It demands fine-tuning the network architecture and lots of experimentation.
Right. This isn't a plug-and-play situation. It's more like trial and error in a science lab, where each experiment might need its own set of tweaks and adjustments.
Absolutely, and that's why understanding the underlying statistical properties and having a solid domain knowledge is critical. Now let's talk hardware. The content really emphasizes that training deep neural networks requires some serious compute power. It contrasts CPUs with GPUs.
Yep.
It's essentially why GPUs are kings in deep learning tasks.
GPUs having tons of simple parallel cores. And it's not just about raw power. It's about the matrix math operations that are intrinsic to neural networks. GPUs are optimized for exactly that.
Exactly. Without GPUs, even a moderately sized network could take an eternity to train. And finally, the success factors. They break it down into three main parts: data and domain understanding, statistical insights, and then the modeling and learning approach itself.
I found that really useful.
It's a reminder that even with the power of deep learning, experimentation remains key.
And here's something I want to challenge a little bit. Sometimes it seems like the article overly emphasizes tweaking architectures, despite sometimes simpler models doing the job well. Would you say that's a fair critique? Not every problem
I'd say
needs
so.
a billion parameter model. Sometimes simplicity can be more efficient and interpretable.
Right. It's a balance. You might go for a deep, complex model if the problem is intricate enough, but for simpler applications, a less convoluted approach might work better.
Exactly. And that's where the art meets science in machine learning.
Also, a quick note on practical applications. The content touches upon a bunch of cool examples, like handwriting recognition, network intrusion detection, and even product recommendations using unsupervised learning. Each of these demonstrates how fundamental these concepts are to real-world problems. It's a reminder that behind our favorite tech features, there's serious machine learning at work driving everything.
And we can't overlook deep learning's contribution to image categorization. With convolutional neural networks, CNNs, playing a huge role here. Indeed, CNNs have really revolutionized the field of computer vision. Their layered approach breaks down images into components like edges, shapes, and ultimately complex objects. Right.
It's fascinating, really, how the network structure, like the number of hidden layers, can affect everything from overfitting to generalization. There's some technical nuance there that's key to achieving high precision, even with massive data sets. You know, it's like crafting the perfect recipe. Too many ingredients might spoil the dish, if not balanced correctly.
And on that note, we should also mention the part about the model defines the features. It sounds almost philosophical, like instead of manually defining characteristics, deep learning models extract the features themselves.
Yes, exactly. It's a shift from the traditional approach of handcrafting features to letting the model learn these features hierarchically from data. That's a huge leap in terms of, flexibility and adaptability in problem solving, although it does make the inner workings somewhat of a black box at times.
Absolutely. The trade-off between automation and interpretability is always a topic of debate in our community.
And let's not forget, hardware is a game changer. The content really drills in that, Without high-performance computing, like those massively parallel GPUs, the training process would be, well, extremely slow in comparison.
Yep, it's like racing a sports car on a bicycle track if you use only CPUs. Exactly. And that's why, in production environments, so many researchers opt for GPU clusters to handle the enormous compute demands of deep neural networks.
Right. And this technical insight not only applies to academia, but scales up to real business applications. So, to wrap up our discussion, this material offers a broad, yet detailed, sketched map across machine learning types, from supervised, unsupervised, to reinforcement learning, plus the nitty-gritty about theoretical principles, and of course, the hardware that powers it all.
Yep, it's a comprehensive dive into the world of machine learning and deep learning. And what amazes me most is the constant interplay between algorithms, data, and computational power. It's like a dynamic ecosystem evolving at breakneck
exactly.
speed.
It's an exciting time to be in this field, with rapid progress and ever-growing challenges that push us to innovate further. Well, thanks for this engaging back and forth chat. It really shows how intricate and interconnected these fields are, from the theoretical foundations to practical real-world applications like intrusion detection and image categorization.
Absolutely. And it's been thrilling discussing all these layers and nuances with you. All right, folks, I think we've covered a lot of ground today, from supervised learning basics to deep neural networks and the hardware that makes it all possible. Thanks for tuning in.